Hi everyone, welcome to the regression analysis lecture. This is one of the subjects at the Statistical Science Study Program, Department of Mathematics, University of Indonesia. So for this session, we will be discussing about model building, particularly for quantitative variables. And then in the previous session, we've learned about how to do model building with what predictor variables, with one predictor variable. And now for this session, we will be focusing on two predictors. Okay, so the template of the model is just beta naught plus beta 1 x1 plus beta 2 x2, but then later on we will see how to put an appropriate or more suitable functions of x1 and x2 that better represent the data, whether we just need to put a first order model or we need to consider model with interactions or probably with second or higher order terms to be put in the model. Okay, so we will be doing that and we just proceed straight away to our simulated data. Again, when you do model building, it is really important to do your data visualization to help you get the idea of the relational relation or functional form of what is it, x and y in your model. Okay, so I've just created some codes to generate the simulated data for our proposed. So I generated the sample of size 100 consisting of two explanatory variables and one of the response variable in here. Okay, so this is the sample data that we generated, and then let's see what kind of relationship that is between x1 and y and also between x2 and y. Okay, so from this scatter plot we can see that seemingly like x1 and y there's just a linear relationship, and the same with x2 and y. Okay, seems like there's no curvature trend, no bending, no something like that. I mean, they're just plain linear form. And so in this case, I will propose the model is that beta naught plus beta 1 x1 and then plus beta 2 x2. Okay, so this is the model that I'll be proposing for this case, and that's called just a first order model. Okay, so this is my model, the first one here. Okay, so this one should be representing the relationship between x1 and x2. Although in this case, if we may add some more information, seems like s1 is better explaining y rather than x2. So probably x1 will be much more significant compared to x2 if you try to run the model. Okay, so now next we will see another issue. Do we really need just to put that thing, or you need to consider interaction terms? Okay, so let's just see. Actually we can just use the data, but then now I generated some new data here, and then again we do the plot just the same like before. In this case, x1 and y seems like a linear trend, x2 and y also linear trend, but in this case is both are positive correlation. So for this model I will expect that beta 1 and beta 2 to be positive. Okay, and then if you think that whether you need to put interaction or not, then you might want to see whether the effect of x1 on y depends on the value of x2 or the other way around. Okay, so that's why here we need to subset our data. So here I just do subsetting. Okay, so the first data set here, the first subset is that where just x1 equals to 1, and then the second data is where x1 equals to 7. Okay, or you can just change the value of the data here. You can see x1 is actually from ranging from 1 to 10. Okay, so for this case I just want to compare these two, and what am I comparing here is that whether I want to see the effect of x2 on y, whether the effect depends on different the level of x1 or not. Okay, so that's why I just choose those two what is it levels, and then so here I do plot of x2 and y. Okay, this is for the whole data, but then if I just look at for x1 equals 1. Okay, because here I'm getting subset 1 is the where x1 equals 1. So this is the relationship between x2 and y for x1 equals 1. Okay, and for x1 equals 7, here this is the relationship between x2 and y for x1 equals 7. Okay, so you can see here different value of x1, the contribution of x2 to y is just the same. Okay, so it means that x2 increased by 1 unit or by some units, then the increase in y is just the same uh, for different level of x1. In just simply saying that the effect of x2 on y does not depend on the level of x1. In that case, then we can say that there is no interaction between x1 and x2. So the model that represents this data should be just the first order model. Okay, now but actually it just makes sense because this is the way I generated it. Okay, so just x1 x2 will put some noise. Okay, so no interaction. Okay, now what kind of pattern that we should suspect that there is what is it an interaction. So let's see something like this. Okay, so I generated just new data, okay, with different scenario, and the data consists of x1 and x2 as well, and the response variable y, and then here I plot x2 and y. So this is the relationship between x2 and y. Okay, so this is for the whole data, the whole sample size. But then if you want to look at the effect of x2 and y, what is it, based on different values of x. Now here, different values of x1, I mean. So we created two subsets. Okay, so the first subset is where x1 equals 1. Okay, so this is the first subset. Okay, where x1 equals 1, and the second subset is where x1 equals 5. Okay, so then do the plot here and see for x1 equals 1, what is the relationship between x2 and y? Okay, still the relationship, we want to assess the contribution of x2 here to y, but only on when x1 equals 1. Okay, so it's represented by the blue line here. Okay, what about um, when x1 equals 5? Okay, so this is how we do it. We want to see the contribution of x2 here to y when using data subset 2, that is when x1 equals 5. And then we have the one represented by the red line here. Okay, what we can say from here, it seems like, okay, for x1 equals 1, then the contribution of x2 towards y is that kind of like negative. So when x2 increases, y decreases, and it's just the same for when x1 equals 5. However, the rate of decreasing is different. Okay, so for x1 equals 5, when x2 increase, then it will decrease y more quickly or much faster than when x1 equals 1. Okay, so in this case, we can say that the effect of x2 towards y depends on the value of x1. Okay, so it means that in that case, we can say that there is an interaction between x1 and x2. Okay, or geometrically, you see that the two lines, okay, are not parallel. In that case, there's an indication of an interaction. So if we see this kind of visualization, then the model that we will be proposing is that we shouldn't put the interaction term between the explanatory variables. So I will put here additional term here, beta 3 x1 and x2, and this is called an interaction or model with interaction. Okay, so that's how you check whether we should put an interaction interaction term in your model or not. And then, okay, you might ask, oh, this is 1 and 5. What if I try something else? Okay, let's see what is. Okay, x1 here is just 1 to 10. Okay, probably what if for x1 equals 2 and x1 equals 9, for example, you do that subsetting, and again we will see whether the effect of x2 on y is different for different level of x1. Yep, we see it's different as well. So then still there's a strong indication that there should be an interaction term to the model, okay? Because the two lines for different level of x1 is intersecting each other here, not parallel, okay? So again, we just need to put the model with interaction. Now, other possible pattern here, let's see something like this. Okay, if you have this kind of pattern, okay, so for x1 is like this, for x2 is like this. Okay, so in this case, seems like there's a quadratic term for x1, while x2 is not really clear, but then probably I'll just choose a simple one that is a first order term for x2, although this is kind of like quite scattered, but not to make it too complicated, I just choose a straight line for x2, but a quadratic term for x1. So in that case, then we will be proposing a model that is here expected y blah blah blah, and then here probably I will just add plus beta 3 x1 squared. Okay, because here we get the pattern something like this. Okay, and this is called the second order model. Okay, so we have the second order model. Okay, so you might ask, can we just, for example, just put okay x2 and just something like this. Okay, so beta naught and x2 and x1 squared. Okay, because why you need to put just x, or while here there's a strong indication of a quadratic. Okay, the answer is no, because we have the concept of what is it? So the answer is you still need to put this beta 1 x1. Okay, you can't just put beta 1 x, you can't just put the quadratic term without the existence of the lower term. Okay, here we have the concept that's called hierarchical model. Okay, what we mean by hierarchical model is that if you put the higher order term in your model, then the lower order term should be included in your model, no matter how insignificant they are. Okay, so when you decide to put the second order model, you also need to put the first order model in your model. The first order term in your model. That's the principle of hierarchical model. Okay, so that's if we have like one of the variable showing indication of quadratic term. Now let's see other trend of the data. Okay, so here again we have x1 and x2 like this. Okay, generate different kind of pattern of the data. And then now probably, okay, seems like x2 is quadratic, right? And then, okay, you have quadratic. Probably, do we need to put like a complete second order model? So now we have the, consideration of complete second order model. Do we need to have something like that? Okay, now what do we mean by complete second order model is that, okay, for example, like this, you have that x1, x2, you have x1 plus x2, and then you have that x1 squared, and then you have that x2 squared. Okay, so that's what we mean by the complete second order model. So all the quadratic terms are there, the interaction term also there, and also the first order term. Okay, do we need to put it like that? Now let's see how do we decide on it based on these plots. Okay, again, okay, it's clearly that the x2 should be like the quadratic, x1 seemingly not quadratic. What about the interaction term? Okay, again, to check whether we need to put an interaction term between x1 and x2, then you have to check whether the effect of x1 on y is different for different level of x2, or the other way around, that is, whether the effect of x2 on y is different depends on the level of x1. Okay, now how do we do that? Okay, so you have to subset your data. For example, in here, I will check on the effect of x2 on y, whether it depends on the level of x1. Okay, so then I will choose x1 on one level and x1 to another level, and then I will fit the regression of y and x2. So this is how we do the subsetting. For subsetting, for the first subset, okay, I choose x1 equals to 1. Okay, that's my first subset data. And then the second subset data is that I will choose x1 equals 7. Okay, you can just choose other values, okay, at least two different values of x1. Okay, then for each of the subset data, I fit the model, okay, of y and x2, and because there is like a clear indication of quadratic, so I put like x2 and x2 squared. Okay, so a quadratic term in here. Then let's do the plot, okay, for different values of the what is it? For the data here, okay, I'll just make it bigger. Okay, so here here we have it. Okay, so this is x2 and y, and this is the blue line here. Okay, where's the blue line? This is the blue line is that the fit of x2 and y for x1 equals 7, and then the red line here red is for subset 1 is for x1 equals 1. Okay, so it's quadratic. Yes, that's true that the relationship between x2 and y is quadratic. Moreover, for different value of x1, seems like these quadratic pattern are parallel. Okay, again, parallelism implies that there is no interaction between this variable and that variable with different level in here, that is x2. So in that case, our model should be just x1, x2, and x1 squared. There is no interaction between x1 and x2. So you can say that this is kind of like second order model, no interaction. Okay. Now, what pattern that we should kind of like suspect the interaction? Okay, here I also have prepared the codes to generate the data. For example, we have something like this. Again, y with two predictor variables x1 and x2. Okay, and then now again subsetting the data, I want to see the effect of x2 on y for different value of x1. So the first subset is for x1 equals 1. This is how we subset the data. And then the second subset is that for x1 equals 7. Okay, and then let's see how x2 and y related for different values of x1. Okay, so this is x2 and y, and then if we check the relationship for x2 and y for x1 equals 1, okay, we got it represented by the red line here. And then for x1 equals 7, we have something like this. Okay, so it seems like, curvature but not parallel. Okay, there will be at some points intersecting each other between the blue and the red line here. Again, non-parallelism, it indicates interaction, because we can say that for the red line, okay, x2 increases, seems like, okay, like downward curvature, but then the rate of increase when it increases the y is slower than is lower for when x1 equals the red one, when x1 equals 7 compared to that when x1 equals 1, the blue line, or x1 equals 7, the blue line. Okay, so just simply speaking, non-parallelism, there's an interaction. The effect of x2 on y depends on the level of x1. So in this case, we put the second order of x2, and we also need to put an interaction term between x1 and x2. So then the model that we should be proposed for that pattern is that we have x1, x2, x2 squared, and here we also need to put beta for x1 and x2. Okay, so second order model with interaction. Okay, that's how we do that. And if you think that, just in case that you have kind of like you think that x1 also showing a quadratic trend, then probably you need to put or you need to propose a complete second order model. Okay, you have the quadratic term for each of the variables, and you also have the interaction term. Okay, so that's kind of like many varieties of interaction or model building for two explanatory variables. Okay, so basically we are done with two predictors.